Okay, hello everyone. Welcome to Mr. Wu's channel. My name is Mr. Wu. Today I would like to share with you my solutions to the 2023 VCAA Methods Exam 1 review. Let's put VCE in there. VCAA VCE Methods Exam 1 and my solutions. So question 1 is a function y equals to x squared minus x all over e to the power of x. The question says find and simplify dy dx. So you need to differentiate this function. This is a classic quotient rule question. So if I go to the formula sheet, if you used the formula sheet given to you in the exam, you are looking at this one here, quotient rule. So if you just apply the quotient rule, you should get something like this. The first line, and you simplify everything. There is here. There is a common factor of e to the power of x at the denominator and the numerator. So denominator and numerator. So you can cancel that, and so on. Here I'll leave the arithmetic on the screen for a few seconds. And then the next question says, function f is sine x times e to the power of 2x. So first you have to differentiate. So notice the little dash here, f dash. So you have to differentiate and then evaluate the derivative at pi on 4. So okay, let me actually write this. So this is quotient rule on your formula sheet. Just follow the formula, and this one to differentiate, it is the product rule on your formula sheet as well. So follow the formula, product rule, differentiate, and you shouldn't simplify anything here because first the question doesn't say simplify as opposed to the first one. The first question does say simplify. Secondly, you need to evaluate it at the end, so which means you need to give a numerical answer at the end. So there's no point, well, unless it's really helpful. In this case, there's no factorizing or simplifying to do. So what I did was I just substituted pi over 4 into the derivative. And here you need to, this is exam 1, so you don't get your notes. So you need to memorize your exact value table, of course, and this one here as well. And you do arithmetic and you simplify. There's a fraction going on, so that's kind of annoying. Actually, even this, I should have written 3 square root of 2 e to the power of pi over 2 over 2. I did rationalize, notice I did rationalize the denominator here. But there isn't really a need to rationalize your denominator. I don't think in the past few years the VCAA marking scheme penalized people for rationalizing denominator. For not rationalizing denominator. You see here, it was a third on the denominator before, so I did rationalize it. But the marking scheme changes every year. The VCAA marking scheme changes from year to year because the chief examiner, the person who decides on the marking scheme, changes from year to year. So it is safe to rationalize the denominator still, but still safe to do so. It is still safe to rationalize the denominator, even though in the past few years it wasn't really a thing in VCAA marking scheme. Okay, and then we have a solving exponential question. E to the power of 2x minus 12 equals 4 times e to the power of x. X is a real number. So here's a trick that you should have practiced. We have practiced a lot. Let some letter a be e to the power of x, because see this is e to the power of 2x and e to the power of x. So that is really e to the power of x all squared. So really it's a quadratic. So what we get is you sub a in here into this bracket, so you get a squared, so a squared, and then I'm moving 4e to the power of x to the left, so minus 4a, a is e to the power of x. Keep the minus 12 equals 0, and then all I'm doing is I'm solving quadratic equation, and then here I've used the cross methods, factorize it, and find my answer for a, convert a back to e to the power of x, and of course one of them leads nowhere because it doesn't make sense. E to the power of x can never be a negative number, no matter what x is. E is the Euler's number. And so that can be discarded, and we are left with the final answer. X is log of 6, log E6. And then question 3, we have a function fx is 2 minus 3 over x minus 1. The question is to sketch the graph, labeling all asymptotes. And then axial intercepts, which I have done here. So this is a transformation question. So you need to realize all the transformations here. So the 2 is a translation in the y-axis, which leads to y equals to 2 as the asymptote. The x minus 1, the minus 1, is also a translation. But it is a translation in the positive direction of the x-axis by 1 unit. So that leads to x equals to 1 as the asymptote. And then of course you also have the negative here, which is a multiplying. It's negative 1 times 3 over x minus 1, which means it's a reflection. So instead of looking like this, we have the red graph, the red one, which is the correct one. So you reflect in the x-axis, or the y value becomes negated. Right, and then you label the points. Well, by that I mean this point and this point. And then of course you label the equations of the asymptotes. Right, so that's the graph. Oh, by the way, I've got this dot here, which is for 1. When I first did question 3a, that wasn't there. Right? So this particular cross here, this point wasn't really labeled in or noted when I first did question 3a. And now explain why this is in my answer now. Because I did question B. Question B says, find the values of x for which fx is less than 1. Well, less than or equal to 1. So to do that, it's almost always helpful to visualize things. And this is the visualization right here. That is y equals to 1. So that horizontal line is y equals to 1. And I need all the f function y value to be less than that, which is where my cursor is pointing at now. The part of the graph of f, the red graph, where my cursor is going through, that's the part I want. So once I visualize this, I can better do the arithmetic, the calculation. So the trick is to find the intersection point between the red curve and the blue line. That's basically the beginning of or the end of function f less than 1. So I made 1 equal to the function. So 2 minus 3 over x minus 1 is the function f, which is equal to, in this case, I want it to equal to 1. So, and x equals to 4. So that's how I know the x value here with x equals to 4, y equals to 1. So I know the graph goes through x equals to 4, y equals to 1, which means I actually came back to question A, erased my graph, and drew it again. So when I first drew it, I think I drew something like let me use this pen here, something like this. Oh, sorry, that's not what I meant to do. I meant to go to this point, but when I first drew it, I drew it something like that. Right? So I did go through the x-intercept, but I didn't go through 4, 1 because I didn't know, right? There's no way of, and there's no need of knowing every point that the curve goes through. So I didn't know the curve goes through the point 4, 1 exactly. But then in question B, so that's when I did question A. But now I do question B, and then I have written when x equals to 4, y equals to 1. So I kind of had to go back to question A and change it. So I did erase my graph, and I did draw it again, going through 4, 1, which means it's kind of a problematic question. Question B, whenever a subsequent question adds more information to the previous question and you have to go back and change your response to the previous question, it's not how a test or a exam is supposed to be designed. That's almost never the intention of any test or exam questions. You're meant to go forward, not backward. So I think this is not the perfect way to write exam questions. Anyway, and then we look at the graph again. So now we know the intersection between the blue line and the red curve, which is y equals to 1. So we need all the red stuff underneath. And the x values for those is between x equals to 1 and x equals to 4. And of course, x equals to 1 is asymptote, so the red curve can never get to x equals to 1. X equals to 1 can never be true on the red curve. So it's a soft bracket on the 1. And since the question is asking for less than or equal to 1, we need to include the point, the intersection point. So x is 4, and then it's inclusive with the square bracket. Question 4. Function is x plus 1 over x. Nice looking curve. And it says use two trapezium of equal width to approximate the area between the curve, the x-axis, and the line x equals to 1 and x equals to 3. So you can see I have drawn x equals to 1 and x equals to 3. The lines. I may as well draw x equals to 2 here, which kind of, if you like, that's the trapezium. I didn't have to draw the trapezium, nor should you actually draw the trapeziums, because that's not really necessary. This is really just a formula question. So you could draw the two trapezium, but it would not be the best use of the time because it is really a formula question. So the trapezium estimate of area has a formula, which is this one here, trapezium rule approximation. So the area is approximately the last x value minus the first x value. Right, so x subscript n just means the final x value, the end of the trapeziums. And x naught just means the first x value over 2n. N is the amount of trapeziums. In this case, it's 2. And you go sub the first x value into f plus 2 times f, substitute the next x value. Right, x naught, x1, x2, x3, x4, they are just 1, 2, 3. They're just the boundary. They are the boundaries between trapeziums. And then everything in the middle is 2 times the f value. But at the end, when you substitute the ends of the trapeziums, the last x value, it is just f. Right? The first and last value is just f. There's no 2 times. Everything in between, there's 2 times. So if you apply this formula, you're just going to get this. The last x value is 3 because the question says so. And the first x value is 1 because the question says so. So 3 minus 1. Right? So 3 minus 1 going here. 2 times n. N is the amount of trapezium. So 2. 2 times 2 is 4. 4 go here. And then I've got f1 plus 2, f2 plus f3. Right? There's a 2 times in the middle and then just f1 with the value on either end. A bit annoying is the arithmetic. You can see here, that's my rough work. F1 is kind of okay because it's 1. When you substitute 1, things are usually easy. And when you substitute 2, not so much. You're dealing with a lot of fraction. When you substitute 3, again, you're dealing with fraction. And you do the arithmetic. It's tedious, but it's not impossible. Finally, you get 31 over 6 unit square. All right. So as you can see, it's really a formula question, this one. Question 4. It's really a formula question. There wasn't a real need to draw graphs, but you can if you want. Question 5, it's an integration question. Integrate from 0 to power over 3, and the function is sine x. Well, if you forgot how to anti-differentiate sine x, it is helpfully in the formula sheet right here. So it's just negative cos, but if there's an ax in the brackets, then you need to do 1 over a. So in this case, sine just becomes negative cos when you antidiff, and you substitute power over 3 and 0 in it, and of course you remember your exact value table, and you calculate, and you get half. And then it says, hence, or otherwise, find all values of k such that integration 0 to power over 3 function is sine x dx is equal to integration from k to power over 2 cos x dx. And then there's also a restriction for k between negative 3 pi and 2 pi. Notice, is there something wrong with my OneNote? Notice, this stuff is the previous question. So it's exactly the same without any variation. It's the same thing, which means this is just half. This is just half. And then the rest of it has the k in it, and you have to find k. First of all, this is a problematic question because it has consequential marks. If you didn't figure out half if you didn't figure out the answer to 5a, to question 5a, let's say you get something weird, right? You get 4 over 3 in question 5a. You can still do it. You can still do question b. You can still substitute 4 over 3 like this, and then equal to the right hand side, and so for k and so on. And you will be given consequential mark and so on, but your life will be very hard because your subsequent calculation to get k will look very messy. Right? If the left hand side of the equation is not the right number, which is half, or there are of course other nice numbers that the question writer could have used, but if you solve 5a and you get a wrong answer, and that isn't one of those nice numbers that can help you solve for k in this equation, in question b, then you can try and do it, and your arithmetic is gonna look really ugly, and you may not even get to any answers. Like it would just be impossible to solve with exact value table. Like you wouldn't be able to solve this with just the exact value table without a calculator. So the consequential marks are problematic. This question would have been better if VCAA said 5a to be show that the integration here is equal to half. In that case, you can use the result in question b and you can still carry on. Otherwise, if you can't do question a, there's almost no hope to do question b because your numbers are going to look very ugly, and without a calculator, relying just on exact value table, you will not be able to get any answer. But let's say you get 5a correct, which is half. Let me raise that. I am now going to only deal with the right-hand side because the integration sign is just ugly. And anytime you see integration sign, you should always try to get rid of it. So I'm going to integrate this, the right-hand side of the equation I'm trying to solve. Cos x becomes sine s. Again, this is on the formula sheet, right about, I It's on the formula sheet. It's right here. And then sub numbers in, including k. K is a variable, but it works as a number. And then you get this, which means 1 minus sine k, which is the right-hand side. Oh, what happened there? Hang on, something's wrong. I think I pressed something. Okay, which means the right-hand side now has been simplified to 1 minus sine k. And then so that's equal to the left-hand side, which is really just a half. So 1 minus sine k equals to half, sine k equals to half. And then from your exact value table and from the domain of k, the domain for k, the restrictions on k, you can work out how many solutions there are. You're just going around in a circle. You're just going around in the unit circle. On the positive side, you go around 1 circle. On the negative side, you go around 1.5 circles. And you get your final answers. Question 6. P hat is a random variable. It's the sample proportion of households that have solar panels. And from a sample of randomly selected households, we have an approximate 95% confidence interval for the proportion P of households who have solar panels. And that 95% confidence interval is 0.04, 0.16. Find the value of P hat that was used to obtain this 95% confidence interval. This is a clever question because it tests you if you understand what confidence interval means instead of whether or not you know how to use the formulas. So P hat, by definition, P hat, the sample proportion, is in the exact middle of any. P hat, by definition of confidence interval, sorry, I should have said that. By definition of confidence interval, P hat, the sample proportion, is in the exact middle of any confidence interval. If you look at the formula itself, it tells you as well. See, that's the confidence interval formula. It's P hat, the first number is P hat minus something, and then comma. The second number is P hat plus something. So you take P hat minus a value, you get the left end, and you take P hat, you plus a value, you get the right end, which means P hat is in the middle. P hat is exactly in the middle of the two numbers in the confidence interval. So, where am I? Which means I take 0.16, I take 0.04 plus, and then divide by 2, which means I get the exact middle value of them, and 0.1. 0.1 is P hat. This is P hat. And then this is exam 1. You don't have the calculator, so in this case, it makes your life easier. Z is equal to 2. Now you may be saying, what is this Z value? Where did it come from? Well, this one, in the confidence interval formula, there's a Z number, and this Z is what the exam question is referring to. Z is equal to 2. So, and then it says find the size of the sample from which this 95% confidence interval was obtained. Again, this is a clever question because if you are not smart in your arithmetic, in your number calculation, number crunching, well, in this case, some algebra as well. If you're not smart, you can still get it, but you will get it after a long time, after a lot of crazy long calculation. Basically, it is just this formula here. Again, formula. So left and right, confidence interval. We know the number, right? So the number is 0.16 on the right, which is this one here. We know what P hat is, we just calculated it. Z is 2, because the question tells us here, Z is equal to 2. And so we have P hat, we have Z, we have P hat, which means we have 1 minus P hat, and we're looking for N. N is the sample size. That's what the question says. Find the size of the sample. find the sample size. N is the sample size. So we have all the numbers. We have all the numbers except N, and we know the whole thing. This whole thing is 0.16, because that's what the question has, 0.16. So put all those in to the formula, and you get this nasty thing. 0.1 plus 2 times square root, 0.1 times 0.9 over N is 0.16. We move the 0.1, we move the 0.1 to the right, so 0.06, divided by 2, 0.03. And here's a tricky part. Not yet. And then we get rid of the square root, so we get 0.03 square, and then the left-hand side. And here is the tricky part. In terms of the arithmetic, in terms of the calculation, number crunching. This is 0.09. Let me write this properly. 0.9. And if you're clever, you will realize it's 0.3 squared. It's 0.3 squared, which is 0.09. So you can get this line here. So all you're doing is not 0.09. What you're gonna do with is I'm skipping a few steps here, right? So you have 1 over n is equal to 0.03 square over 0.3 square, because I'm just dividing the numerator, the top. So which means n is 0.3 over 0.03 square, but this is not good writing. 0.03 over 0.3. No, that's not what I meant to write. That's what I meant to write. Now you reciprocate everything. And that leads to my next line here. Because you have the numerator square over denominator square, it's really the whole fraction squared. Just 0.3 over 0.03 squared. And this is clever, because 0.3 divided by 0.03 can be easily evaluated. It's 100. Hopefully you can see that there's a difference of 0 between the numerator and the denominator. Sorry. What I meant to say is, again, I'm skipping steps. This 10 square, hopefully you can see that. Because 0.3 divided by 0.03, well, there's a factor of 10 in between. And 100. And then we get 100. So if you're not careful, you would, if you evaluated the squares, so if you didn't keep the square and you turn this into 0.0009, and if you turn this into 0.09 without turning it back to 0.3 square, you would spend a lot of time calculating numbers. But if you leave everything in squared and not evaluating the square operation, and then realizing 0.1 times 0.9 has a different representation, then your life will be easier. Okay, and then they are now selecting a larger sample. The sample size is 4 times. It is 4 times the original sample. And then it says the sample proportion that is found is the same as before. By what factor will the increased sample size affect the width of the confidence interval? Right, so this. Between 0.16, it's like this. Between 0.16 and 0.04, our previous confidence interval, there is a certain width between them. And now it says, well, if I select 4 times the original sample size, what's going to happen to the width of my confidence interval? Well, it's really a formula question, because the width is just this. If you let me actually take this. Yeah, I'll take a screenshot of this. That's the formula. That's the formula. So you're taking p hat and you minus this monster and you plus this monster, right? So the width is really just 2 times that. 2 times the monster. Right? So the width itself, the width for any confidence interval is really 2 times z, because you have the p hat in the middle, and then you minus this monster to get to the left endpoint, and you plus the monster to get the right endpoint. So there's a 2 of the monster in the entire width. So 2z, and then p hat 1 minus p hat, and then n. But if n is your original sample size, and now you 4 times it, and now you 4 times this, so you get a new width. Your new width is going to be 4 times that, 4 times n. If n is the original sample size and you 4 times it now, you still get a width of confidence interval, but now it's slightly different. You have an extra 4 in it. But notice, this is really, what am I trying to do? P hat 1 minus p hat, and then n. Okay, you can take out the square root 1 over 4, because 4 is really 1 over 4. It's dividing by 4, right? It's dividing by 4, so it's really 1 over 4 in square root. Because if you multiply the 2 square roots together, the 1 over 4 just go into the fraction, go into the bigger fraction. If you multiply the 2 square roots. And that is just that. Square root 1 over 4 becomes a half. So everything else, 2z, and then this monster here, that's all the same as the original width. So all you're doing is the original width times half. So the factor is half. The previous width of the confidence interval is halved. It's a smaller confidence interval, which is a good thing. It's a good thing to have a smaller confidence interval when your sample size is increased. Right? If you have more sample, you expect your confidence interval to be smaller because you're more confident. I shouldn't say that. You're still 95% confident, and your 95% confidence interval is narrower, becomes narrower. Okay, so this is another formula question. And question 7. There's a domain restriction for negative infinity to 1, and the function is fx, and it's x squared minus 2x. The graph is shown to you. Ignore the red part. The red part comes later. So all we're given is the blue line. The red one is what all we're given is the black curve. The red curve, I did that later. Okay, and then the range, well, you basically sub 1 in, and you find the endpoint here, and you can see that is the lowest point, and the y value is -1, so -1 to infinity is the range. And then it says sketch the inverse. Remember, inverse is x and y swapped. X becomes y, y becomes x. So 1, -1 becomes -1, 1, -1, comma 1, and you just draw that in. The black curve goes through 0, 0, which means the inverse goes through 0, 0 also. and you kind of also know that the inverse is meant to be symmetrical around. I need to draw a better graph than that. Your inverse and the original they are symmetrical around the line y equals to x. And so visually, that's what you do. You take this point, for example, a negative small number 1, and so you go 1 and then a negative small number, so on and so forth. Oh, actually, this point is good to use. -1, 3. X is -1, which means that's going to be the y value, and y is 3 here, which means that's going to be the x value. So x is 3, y is 1, y is -1 on the red curve. Okay. Determine the equation and domain for the inverse function of f. Okay, here's a tricky part. You have to write this line, you have to write let, and you have to say y equals to this. It's not safe to not do not y equals to fx. Don't do that. That may or may not get you the mark. You should, of course, it makes sense, but it is not the safest option. The safest thing to do is to write out the rule of the function. So y equals to x squared minus x. Do not write y equals to fx, f of x. And then you need to write this line also. So you need to write this line, and you need to write this line. That looks like 20. It's 2. To get inverse, swap. You need to write swap x and 1. And then you get the next line. The next line is x equals to y squared minus 2y. Okay, so the first two lines you have to write. Let y be the rule of the function, and to get inverse, swap x and y. And, well, your goal is y equals something, right? Your end goal is to make y the subject, and you make y the subject. But that's easier said than done because y appears twice and it's a quadratic. What you will have to do is not to factor out the y. If you factor out the y, you still get y appearing twice, so you still can't really make y the subject. You need to complete the square. So here, I'm just completing the square right here. I did that because that let me achieve the appearance that y appears once. Right? By completing the square, I have made y appear once, which means I am getting closer to making y the subject. So move the negative 1 to the left, x plus 1, get rid of the square root, get rid of the square, which means a square root, and then y minus 1. And whenever you take the square root, you have plus and minus, two options, and you need to consider which one to keep. Because the domain of the original is negative infinity to 1, the domain of the original becomes the range of the inverse, which means we want the negative option of the square root because we want negative y values more than positive, really. And we say which option we keep between the positive and negative, and we change notation to inverse of f, and the domain of f, we state that to be negative 1, infinity, because that's what it is. Now you look at the range of the original, that becomes the domain of the inverse. And then it says calculate the area of the region enclosed by f, inverse of f, and y equals to negative x, negative. It's easy to miss the negative. So visualize, of course, always visualize. I'm going to erase this now. Y equals to negative x. It has to go like this. Y equals to negative x. Equals negative x. Of course, I didn't draw the inverse function perfectly like a machine because I'm not a machine. So my curvature here isn't really what it's meant to be. It's meant to be like the black one. So even though your drawing is not going to be perfect because you're drawing by hand, you're not drawing by a computer, you should realize you really have two areas, and they're symmetrical. They're symmetrical about y equals to x. So you have two areas, and they're the same. They're the same area, and there's two of them. It doesn't look like it, but the curvature of the red one is supposed to be the same as that of the black curve, and the blue one is a straight line. So realizing that, the first thing I wrote is to treat the two areas separately. So from negative 1 to 0, so that's the x values, right? From negative 1 to 0. I need to treat them differently because they are bounded by different curves. So this is the blue and red, but then this is the blue and black. So I need to treat them differently because they involve different functions. Like this, negative x minus inverse, and then between x equals 0 and x equals to 1, negative x minus f. But then I quickly realized this, to anti-diff a square root, it's possible, of course. It will be a kind of a good exercise for you to try. It is good to, well, it can be done in NTD square root, but it will take a long time. The calculation gets more involved and complex, which means it's easier to make mistakes also. So it's prone to mistake and it takes longer. So then I realized, let's avoid that. Just take the easier integration times 2 because it is times 2. The area is the same area times 2. So I took the easier integration from 0 to 1 and then I times 2. So evaluate, I get a third, which is the unit, a third unit square. That's done. Question 8. You have a queuing time. T is the time in minutes. And the probability density function is F. And there's a K times T times bracket 16 minus T squared close bracket. And K is some real number. And you have to show K is 1 over 64. The trick here, not trick, the rule here is you must pretend you don't know the answer. The answer is K equals 1 over 64. But you need to pretend you don't know that. And you work out the answer from scratch, from nothing. Also, here's a tip. I've given you this tip before. Do not evaluate indices until the very last step. It will be much easier to simplify if everything is written in index form, like this. To find K, the condition of a probability density function is that the whole area underneath it has to be 1. So that's what we do. We integrate from 0 to 4, the domain of it. Integrate the probability density function and we make it equal to 1 because it has to equal to 1. So the K value has to give area 1. And expand the brackets because it's easier to additive polynomial. Additive sub in 4 and 0. Now, look at this. dt. T is the variable. T is the variable. K is a constant. They're different. They mean different things. K is a constant. It means K doesn't really change. K is unknown. They are both. Actually, I shouldn't even really say that. I should just say this. K is unknown, but it's a constant. T is a variable. Right? Variable and constant are different things. Variable means T can change. K means it cannot change. Well, it could, but constant means in principle, K is not changing. K as a value is not changing. We just don't know it yet. We don't know what K is, but it's not supposed to change. T is a variable, which means T can change. Which means when I do the integration and I sub in 4 and 0, I'm subbing in T. I am subbing T. T takes the value of 4 and T takes the value of 0, not K. K is a constant, it doesn't change, it stays there. So it's like this. Right. The next step is I am breaking the 8 into 2 times 4, and then T squared becomes 4 squared. Over here as well, so KT to the power 4, which becomes K 4 to the power 4 divided by 4. Well, I'm skipping a few steps. So 4 to the power 4 divided by 4, I've written that as 4 to the power 3. And here, 8, I have written 8 as 2 times 4 because I know there's a 4 square happening. So if I have a 4 here, then everything is in the same base. And then I quickly realized 4 times 4 squared is 4 to the power 3, which is here. So I can divide everything by 4 to the power 3. So I'm left with 2k minus k equals to 1 over 4 to the power 3. And of course, k is 1 over 64. So arithmetic can be simplified if you only evaluate powers at the end. And then I'm finding expected value of t, which is really, I should have written this. T is really the, I'm just going to write the generic one. Negative infinity to infinity dt. Right, so expected value of a continuous probability function It's the variable times the function itself, integrate over the whole domain. So in this case, the domain is 0 to 4, but I have times t here already, so t squared. So basically, this one, I'm taking this one here, kt 16 becomes kt squared 16, because I'm multiplying everything by t, and t cubed becomes t to the power 4. So here, I'm using k, I'm not using 1 over 64, because it's just difficult to write. So I'm just using k here, and I sub for, again, 4 and 0, they are t values, they go in, and then I change k into what it really is, 4 to the power of negative 3. K is 4 to the power of negative 3. So here, k is replaced by 4 to the power of negative 3. Same thing here. K is replaced by 4 to the power of negative 3. But you can see the magic here. Oh, by the way, I've turned 16 into 4 squared, because that's going to be helpful. And then everything is in base 4, and I can simplify the powers, the indices. So 4 squared over 3, 4 squared over 5, and final answer. So I am avoiding dealing with large numbers. I'm never going to evaluate 4 to the power 5. There's no way I'm calculating 4 to the power 5 on the spot in the exam. Or even if I know the answer, I'm not going to write it down. It just makes my life harder, not easier. So it doesn't matter if you know the answer to 4 to the power 5. You're just not going to do it. Okay. And then it says, what's the probability that a person has to queue for more than 2 minutes, given that they have already queued for 1 minute? Again, the question itself is just a conditional probability question. So t bigger than 2 given t bigger than 1, but the intersection between t bigger than 2 and t bigger than 1 is just t bigger than 2 over probability of t bigger than 1. You can calculate each. Each one is totally doable. You just integrate between 2 and 4. With the k value known, you know the k value, so I've kind of just substituted in here and get the answer. And you calculate probability of t bigger than 1, which is integrate from 1 to 4, same function, you get the answer. But as you can see, you get some ugly fractions going on, and you have to sub them back into a bigger fraction. So it's a fraction on top of a fraction. All I've done here is 9 over 16, which is here. Instead of dividing by probability t bigger than 1, I'm multiplying the reciprocal of it. Right, so when you are dividing by a fraction, you can multiply the reciprocal. So 256 over 225. And you simplify, and you get 16 over 25. So it's very doable, but personally, I'm not really happy about the amount of arithmetic involved in this question. There's just too much. I don't believe it belongs in exam 1. It will be better suited for a exam 2, for example. Okay, question 9. You have 2 walking tracks like this. And the first one is f. There's an a value in it, which is unknown to us. Minus x, bracket x minus 2 all square, which is if you look closely, this is a cubic because x times x squared. So you can tell it's the solid curve. That's what I've done here. I'm telling myself it's a solid curve. And then number 2 track is the function g. This is 12x plus bx squared, so it's a quadratic. And you can tell which one of those is the quadratic. So it's the dotted one. So the dotted curve, I've indicated that it's g. And all units are in kilometers. Some more information given to us. When x is 0, f is 12. When x is 1, g is 9. Verify a is 12, b is negative 3. I am personally confused by the word verify. It's not a word that VCAA used often. I struggle to find a case in the past few years where VCAA had to use this word in their questions. So I don't know what it means. Usually we see show questions. Show questions are commonplace. So I don't know if verify is purposefully different to show, if they mean different things. I'm not sure if students are allowed to sub in, so I'm not sure they are allowed to assume they know the answer and substitute the answers in, and then compute f of 0 and check what that is, and compute g of 1 and check what that is. Usually in a show question, you are only to assume you don't know the answer. So that's what I'm going to do here. I'm going to assume I don't know the answer. I'm just going to put 12 equals 2 and then take f and then substitute x equals 0. And that's all I've done here, and I have proven that a is 12. The next thing is 9, so 9 equals, and I'm just substituting x equals to 1. And then I do some calculation, and b is -3. So I have done this in a show way. So assume I don't know the answer. No, there's two answers here, so I use plural. But then again, I really do not know what verify means and what difference it has with the word show. As of the recording of this video, the VCAA has not published their examiner report of this exam, so I'll have to wait for that to come through. And then the word verify again, verify f and g both have a turning point at P, highlight turning point, and then give the coordinates. And then here's my query also. For a 2-mark question, I am not sure if we need to prove a stationary point is a turning point, right? So stationary point just means the derivative is equal to 0, right? Which means there are really 3 types of stationary point. This and this, local maximum, local minimum, and stationary point of inflection. And so, which means simply finding the first derivative, make it equal to 0, and solve for it, just proves it's a stationary point. It doesn't prove it's a turning point, because turning point is one of those two. So I wasn't sure if we are only required to do the first derivative, make it 0 and solve, in which case we're only finding stationary point and we're not proving turning point. Or do we have to prove it's a turning point? We can do that by either using the second derivative, which is, by the way, not in the side design. The side design has second derivative, but the proving of nature of stationary point using second derivative is explicitly not in the side design. So that's the common way of doing it. The most common, and to me the way that makes the most sense is to use second derivative to prove the nature of stationary point. But that's not in the side design, so I wasn't sure if we needed to do that, or we do a little table to show the nature of stationary point. Right? So what I mean by that is like a table like this. So you got an x value, right? And then you have your actual answer. What's my answer here? X equals 2, right? So you have x equals to 2, and then you pick a point to the right, pick a point to the left, and then you do like a f dash here, and right, and then so here it's derivative is 0, and then what's going to be positive, negative, yeah. So maybe this is a 4, this is a -3 or something. Actually, it's going to be the same. Not for f. Not for f. Yeah, so it's okay if I do like a -3 here. Positive, negative. Yeah. Yeah, there you go. It's flat here. It's going up and it's going down. So we can do a table like this. And then we know that when the table comes after I find the answer. So when I solve the first derivative equal to 0, I get x equals to 2. When I solve the first derivative equal to 0, I get x equals to 2. So I'm not sure if we needed to do a table like this to show that when x equals to 2, the derivative is 0. But then to the left, the derivative is positive. And to the right, the derivative is negative. Therefore, it's a turning point. And specifically a local maximum. Yeah, so I wasn't sure. But anyway, that's all I did. I expanded the function of f to make it a straight polynomial, differentiate it, and then make it equal to 0. Solve for x. I get two answers. And then I kind of know which one is the right one because you can just look at the graph. The first one is not it. You want the second one. You want the one that's common in both graphs. So I take x equals to 2, sub it back in my original f, and I get the y value. And I take the g function, differentiate it, make it 0, solve for x, which is 2, sub 2 back into the original function, get the y value. So it's the same coordinates, same point, right? So f and g independently, finding them independently, have the same turning point, 2, 12. Well, the same stationary point, 2, 12. And I have just turn it around and said it's a turning, not turning around, like I have just said it's a turning point. Really, all I've done is stationary point. So I haven't really proven turning point, but I've just said that. I've just said this point is a turning point and point P. So the question says point P. So point P is 2, 12. So this sort of stuff, this sort of table here, I will have to wait for the examiner report to come out to know for sure whether or not that's needed for a 2-mark question like this. If it's a 3-mark question, then I will most definitely do it, but it's 2 marks, so I am not sure. And then you have the theme park. It will be a triangle, OAB. O is the origin, A is some point on the x-axis, and it tells you the coordinate. It's k, 0, and then we don't know what k is. But there's a restriction on k between 0 and 4, exclusive. And then point B is on the curve, the dotted curve, and it's curve G. So x is the k is the x value, and then the y value is gk. So first we write down what gk is. So the point B, which is just substituting k into the function g, and then we construct a area function. So let A be the function area. So area of triangle. I think it's on the formula sheet if you ever forget. I think here, right here. Half times space time, oh wait, that's not what I want. That's any triangle. Is there a right angle triangle? No. Okay, so this one is for any triangle. Doesn't have to be a right angle triangle. You can always use this formula. But here it's a right angle triangle, so let's just use that. Base times height times half. And that's all I've done. So the base is k, because from O to A, the distance is k. The point O is the origin. So the base length is k. The height is the y value of B. The y value of point B is the height of the triangle. So that is just 12k minus 3k squared, and then times half. And I expand the brackets and simplify things, so I get a shorter function. And then to find the maximum, to find the maximum of anything, maximum or minimum of anything, you almost always differentiate, and then you make it 0. You make 0. Almost always. Of course, there's a difference between absolute maximum and local maximum. When I say almost always diff, that's the caveat. Sometimes the maximum is not at the turning point. Sometimes the maximum is a absolute maximum, which may or may not be a turning point, a local maximum. The absolute maximum may not be the local maximum. But in this case, we should be all right. I'm gonna diff the area function, make it equal to 0, and then solve for k. K equals 0 is not our answer because k cannot be 0; it's exclusive. So k must be 8/3, and then I take 8/3, sub it back into function A, the area function, and do some calculation. Again, if I look at my calculation, oh yeah, so I have sub 8/3 into this one here, into the original area function, but I realize there's a common factor of 8/3 all squared, so I take that out, and I'm left with 6 minus 3/2 times 8/3, because there's a cube here, I'm only taking out a square. And so the arithmetic is slightly easier this way. By taking out a factor, I can deal with smaller numbers. But then again, look at my comment. I am not thrilled by the arithmetic. I don't think it's necessary. And the question feels like an exam 2 question. And I say this because if you want to be very pedantic and very sure, you kind of have to graph this function and see with the domain, of course, with the domain, graph this function with the domain 0 and 4, and see if the absolute maximum agrees with the local maximum, which you can do. I don't think I want to do it now. Actually, let's do it now. Why not? K is k squared 6 minus 3 over 2k, right? Yeah, so the x-axis are gonna be k when a is 0. I have k is 0 or k is, well, let's do it like this. Because of 6, k is 12 over 3, 4. So I'm going to get something like this. This 0, this is k, this is a, and that's going to be 4. And let me see. And then I am expecting a k equals 0 and that. And it's a cubic. So it's gonna get more. No, sorry. It's a cubic. Yeah, sorry. I'm looking at this. Sorry. K squared. It's gonna be like this. It's gonna be like this. The more positive the k value gets, the more negative here it gets. Yeah. And then, of course, I have my endpoint, so it's going to be... Oh, sorry, let me explain myself. There's a turning point at 0, at k equals 0, because it's a k square here. Right? If the function has a k square times bracket, the x-intercept that results from k square, which is 0, is we know that's a turning point. And then which means the other x-intercept, which is k equals to 4, the curve just goes through the x-intercept. And so indeed, and then also, I know it's not going to be like this. It's not going to be like this because it's a negative k cube. Right? There's a negative k cube, so that tells me the direction of the cubic. If you have a very big positive k value, the negative k cube will dominate everything else. This term, the negative k cube term, will dominate everything else, and the whole area will become negative. So that gives me the direction of the curve. So yeah, so if we have the domain like this, it is going to be like that. Then is the first drawing was better. It's going to be like this, and so we're okay. The point where k is 8 over 3 gives the absolute. This one here, I didn't mean to draw it like that. That's not a. So this point here, 8 over 3, that will be the local maximum as well as the absolute maximum. So the area here is absolute maximum 128 over 9. Just to make sure. When we divide, make it equal to 0, the answer we get is not a. Well, the answer we get is a local maximum as well as a absolute maximum. Okay, that's it. If you have any questions, feel free to leave it in the comments. I may get a chance to respond. Thank you.